I think they're just walking around. So it's really my privilege to introduce our today's speaker that is coming from Los Alamos National Laboratory, and I will try to read in small print in terms of your
Don't feel obliged to read the whole thing. It's looking quite long.
Christine Anderson-Cook has been a research scientist in the Statistical Science Group at Los Alamos National Laboratory since 2004. She currently leads projects in the areas of sequential design of experiments, non-proliferation, and effective costing of data competition, and we will hear about it today. Before joining Los Alamos, she was a faculty member in the Department of Statistics at Virginia Tech for 8 years, and before that she was in Canada, actually born in this country. Her research areas include response surface methodology, design of experiments, reliability, multiple criterion optimization, and graphical methods. She has authored more than 200 articles in statistics and other peer-reviewed journals, and has been a long-time contributor to the Quality Progress Statistics Spotlight column. She also co-authored a popular book on response surface methodology with Raymond Myers and Douglas Montgomery. Again, she served on many editorial boards, not to read all of them. And she is an elected fellow of the American Statistical Association and the American Society for Quality. From this American Society for Quality, she received several awards and medals. And in 2011, she received the 26th Annual Governor's Award for Outstanding New Mexico Women. So congratulations to you.
So from the introduction, you probably figured out that this is not going to be your standard nuclear engineering seminar. So I'm going to talk a little bit about a 3-year project that I've been a part of that hosted 2 data competitions, where the focus of those competitions was in urban radiation detection. And so I've tried to highlight some of the pieces that will be relevant for this audience. But it's been a collaborative effort, so Lulu at the University of South Florida has helped with some of the statistical methodology development. Carrie Myers, my colleague at Los Alamos, was the original head of this project, and then she got called into management. And then there's a team of folks at Oak Ridge and Berkeley Labs up the hill that have been working on this as well. And so feel free to jump in if something needs clarification. I'm very happy to be interrupted. And so I'll sort of walk through some of this with sort of describing the competition, describing some of the statistical elements at a high level, and then also being able to talk about the results of the competition and what we learned about the algorithms that were developed as part of that. Okay, we have this notion that competitions are a new thing, and it turns out that that's not actually correct, that data competitions are relatively new. The Netflix competition in 2006 was really the first one that presented data to competitors. But before that, there were a number of quite important competitions that were hosted, and I'll tell you a little bit about them, and that will also motivate some of why competitions are such a powerful vehicle for revolutionary change. So in 1714, the Act of Longitude was something that was posed by the Royal Observatory Society in United Kingdom, and they were looking for a method for being able to estimate longitude. So they had already been trying to solve this for more than 3 decades. It's an era of exploration. Longitude is very important. If you're going to sail your ship through the night, it's very helpful to know where you are so you don't crash into land. And also there's a lot of map building that was going on. And so the winner, John Harrison, was a village carpenter. Okay, so they were not expecting a solution to come from that. They thought the astronomers were going to come up with this solution. And his solution was a very precise time measurement device that could keep accurate time on a rolling ship. So with that, they were able to figure out what longitude people were at. But this is some of the message of competitions. You're going to get innovative solutions from sources that you're not expecting. 1810, food preservation in France. The winner there was a chef and confectioner. And his solution was so innovative that the canning processes that we use today are still using the key elements of that solution. So here is a solution that survived over 200 years that came out of a competition. The Ansari X Prize, you probably heard about that. This was an incentive to get private companies into space. So a couple of dozen companies vied for this prize. And it really has transformed our notion of what space exploration is going to be about. It used to be something that big governments were financing, and now we've got a number of companies that are making forays into that. And so this has been revolutionary in terms of how we actually tackle getting these innovative solutions. The Netflix competition, in terms of the criterion that they posed, was very successful in terms of being able to use the solution, an utter failure. So they spent $1 million, they had all these competitors, and what they got was a solution that was so complicated that there was no hope of implementing it. So this one comes with a warning of be careful what you ask for. So they asked for a solution with a level of accuracy, but they never specified any computational requirements to actually achieve that. The last one, Bill and Melinda Gates Foundation. This is a $1.5 billion prize, still unclaimed as of this time, where they wanted to offer some incentives for developing cheap and effective vaccines for diseases that are common in third world countries. And the idea is that the patents that are currently offered for pharmaceutical companies are not enough incentive for them to pursue solutions in this realm. And so with this, this amount of prize money is incentivizing pharmaceutical companies to actually develop things. So this are all from a book by Tim Harford, Adapt, where the idea is that a lot of the transformational discoveries that we need for the difficult challenges that we're facing these days are not going to come from incremental development. So grants and other funding agencies are not an appropriate vehicle a lot of times for these revolutionary changes. Okay, so I mentioned a few of these. What are some of the benefits of competition? In the context of our urban radiation search competition, we were chasing after all of these aspects. So the crowdsourcing, we wanted to bring different people with different expertise worldwide into our competition sphere and see if they could generate some innovative solutions. The competitive fervor is also very helpful. You notice some big prize money offered in a lot of those competitions. You're going to get different people participating when there's prize money. And here is a plot of our second competition, which started in March a year ago and went through to mid-April. So in 6 weeks, each one of those dots represents a solution that was submitted by a competitor. And you can see as we get close to the end of the competition, there is just a frenzy of activity. And so we tend to see accelerated improvements to the algorithms just because of the competitive atmosphere that we fostered with the competition. The third one is something that rarely gets talked about. If you read papers in the literature, what you read is that someone proposes a new algorithm, and lo and behold, they present a study that says, look, ours is the best. And all of these papers have an element of that. And yet it's very difficult to figure out, for your particular problem, what is the best algorithm. And so this allows the host of the competition to put forward a question and a data set where they're interested in the outcome, and then people need to respond to that data set, and you get a clear ranking of which of the solutions are best for the problem that you have. And then lastly, it can be a recruiting tool, being able to draw people in. Walmart and some other companies are now using this as a hiring strategy, give potential job applicants some data to look at, and then depending on how well they come up with solutions, they decide through that whether they want to interview people or pursue them. So a lot of creative things that can come out of data competitions. All right, a little bit about what the rest of what I'll be talking about looks like. So for those of you who have not been a part of a data competition before, I'll just explain some of the mechanics of how they're set up. Then I'll describe the two data competitions that are in the realm that you are all familiar with, urban radiation search. And then I'll talk a little bit about the design of the data competitions. So choosing that data set that we put in front of the competitors is a critical component to our success. And so how did we tackle that? And I'll propose a new kind of space-filling design, which is actually much more broadly applicable than just data competitions, that gives the user, the person collecting the data, a lot of control. We did a post-competition analysis for both of the competitions, and so this allows us to really understand what happened with the competition. It takes us beyond sort of the ranking that we got from the leaderboard and understand the strengths and weaknesses of the different solutions. And then lastly, I'll talk a little bit about the results of our competition and how we feel that we've moved the needle a little bit in terms of the search algorithms that came out of this. Okay, so data competitions, this is pretty universally applicable. If you go to Kaggle, most of them are structured this way and a number of other ones. So we start off with some available data. In our urban radiation search competition, we were using simulated data from a model at Oak Ridge National Lab. And so one component that we present to the competitors is a training set where both the inputs are provided, but also the answers. So this gives them some sense of what kinds of answers we're looking for and the structure of them and something to train on. And then we have a test set where only the inputs are provided and the competitors are going to be providing the answers. So this looks like a lot of data and analysis kinds of metrics. But what the subtlety that comes into this is the test set is actually divided into two sets. So there's a public test set. So while the competition is running, every time they submit their set of answers, they're getting feedback. So was this submission better or worse than the previous one? How does it compare to everyone else in the competition? So they're getting feedback on a portion of the data, and then the other portion is the portion that we're going to use to choose the actual winner. So the people who get prize money need to perform well on the private test set data, and so that can have different characteristics than the public test set data. The catch is the competitors receive the test set data all in one group, and so they don't know whether a particular run is contributing to the public or the private component of their scores. The leaderboard scoring takes all of the elements that are important to us in evaluating the algorithms, and it bundles them into a single formula that needs to be decided before the first competitor submits their first solution. So we have to commit to what our priorities are for the competition, and we're going to use that for ranking. And the structure of this leaderboard scoring is generally the same between the two competitions, or the two data sets. There's usually some other rules aimed at preventing competitors from gaming the system. You could imagine if we have 25,000 runs that we're presenting to the competitors, if they could look at things one at a time and submit hundreds of thousands of submissions, they would be able to figure out something that we don't want them to figure out. We want a global solution that we can apply to a real operational setting. And then sometimes there's opportunities for teams to collaborate and combine their efforts. Okay, so that's sort of the basics of data competitions. Now I'll talk a little bit about the competitions that we hosted that are in your space of urban radiation. All right, so Oak Ridge had a simulated model that was based on a half-mile stretch of street. So here is an aerial view of the actual street that was broken into components for different buildings made out of different materials, sidewalks, roads, a variety of components. And we have the ability, through a number of parameters, to vary the natural background radiation that we have through KU and TH. So this setup was used for both competitions. So the summer of 2018, we held one for government employees only. So these were mostly folks at national labs and their collaborating partners. Got nearly 1,000 submissions. And then a year ago at this time, we hosted one on Top Coder which is a forum like Kaggle, where they host international competitions open to everyone. And so we had more competitors and about 1,600 submissions for that. So what did the data look like? So it was list mode data. So the training set had about 10,000 runs, where here is the start of one of the runs. So we have a time between events, and then we have what the event corresponded to, and it was a photon being received at a detector, and it was designed to mimic a thallium-doped sodium iodine detector. And so we have an energy associated with that photon. So picture a very long file, photons arriving at the detector with an associated energy. All right, the test set consisted of about 16,000 runs, split between the public and private components, and we provided an energy spectra for each of our 6 sources to the competitors. So here are the 6 different sources that we wanted them to find. Obviously, their uranium and plutonium are the ones that we're going to get most excited about, but we are also interested in the competitors' ability to distinguish between these ones and medical and industrial isotopes. Your response, if you're seeing a medical isotope on the street, is very different than if you're seeing some weapon-grade plutonium. And then the last one was sort of a hybrid, a combination of uranium and technetium, to see if someone might try to, an adversary might try to mask the uranium with something more benign. So we're interested in being able to figure out which of those they were. So for a particular run that had a source in it, we want the competitors to say, I found something, detect. We want them to say what it is, so identify which source it was, and then also tell us when the detector was closest to it. So go look here, this is the moment you're closest to that. We also had a number of runs that didn't have a source in them, and we wanted people to say we didn't find something. So as you know, with all of these detection algorithms, a high false positive rate will effectively render the solution useless. If an alarm is constantly ringing, people are just going to walk away from that as an algorithm. Okay, so that's what the data look like. I told you a huge number of runs, about 25,000 runs total. And so here are the things that we could manipulate. We wanted to exercise these algorithms over a wide variety of conditions. So we had 8 different background models. So that really corresponds to different versions of the streets. So we permuted the blocks so that they didn't always come in the same order. In the source category, we had 6 sources. We had shielded or not shielded. So sometimes it was blocked by a metal box or the equivalent. The strength, so how much material was there. And then we had a variety of locations on our blocks that where the source could be located. We also varied the speed of the detector. So we have a detector driving up and down the street. Sometimes it would go at walking pace. Sometimes it would go at moderate driving pace. We also changed which lane it was in. So this is a 4-lane road. And just to make things look more different for the competitors, we started and ended the path at a variety of locations along that route. So lots of different variations on this, and what we wanted was an algorithm that was robust to all of these pieces and be able to do detection under a variety of backgrounds. Okay, the design of the data competition, how can we be strategic? And I'll talk a little bit about how we actually generated 16,000 test set runs in an efficient way, given all of the parameters that we were trying to manipulate. So here are the strategies that we outlined. Some of them are technical, some of them much less technical. The first one, we're holding a data competition to attract new competitors. So let's not put obstacles in their way. So if a data scientist knows nothing about urban radiation search, let's make it easy for them to make that first submission. Let's give them everything that they need to know to get started, and then they can put the power of their experience to work for solving this new problem. The flip side of that is people with your experience, we don't want to hand them a data set that looks completely different than their realm of experience. So for the subject matter experts, we want it to be familiar enough that people with expertise can get started. And so that's the balancing act that we want to get diverse technical backgrounds. My training is in design of experiments, so there's a lot of theory us how we should design a good collection of data to answer a question. But now we need to change our way of thinking about that to having an adversary. So our adversary here is the collection of competitors. The competitor doesn't care that we want to have a good algorithm. They want to just get a good score. So we can't put artifacts into our data that they will use as cues to solve the problem that have nothing to do with fielding an operational solution. And so we have to be very careful and adapt our replication and randomization and balance so that we're actually facilitating a good solution from our adversaries. So for example, in balance, we have these 6 sources. A good designed experiment would have equal numbers of runs for each of those sources. But that could be something that a competitor could leverage. If they have one easy source, oh, there's exactly 1,000 runs for that source, they might assume that there's 1,000 runs for the other sources, and that could give them some advantage that has nothing to do with the solution that we want to have. 3, 4, and 5 are all about fielding the right set of data. So first, we're going to need to define ranges for all of those parameters that we're looking at, and then actually target those regions. We also want to emphasize data that's of maximum interest. Imagine that there's a run that is just completely obvious, and every competitor gets that right. We haven't learned anything. If we have a whole bunch of runs that are too hard and nobody gets them right, we also haven't learned anything. And so we want to have the region where there's differences between the algorithms. We want the majority of our data to be located there. We also want to discourage overfitting by the competitor algorithms. And so we want regions of interpolation and also extrapolation. And you'll see as we look at the data sets, how we've encouraged both of those kinds of demonstrations for the algorithms that we have. Okay. And lastly, we want to create a leaderboard scoring that actually gets the proportion of runs for our different criteria to match what we have. Okay, I realize I jumped ahead here, and so I forgot to show something. So here is a movie of what one of the runs might look like. So here is our street, and our detector is moving along the street, and here is a summary of the counts that we have for what the detector is picking up. Obviously, there's some spectral information that we're hiding here, but in this case, I chose a run that was very much on the easy side. And so as this goes along right about here, you'll see a big jump. So this is not one where it would be difficult to figure out what was happening. We still have some extra work to do. We've detected it, but we have to identify which of the 6 sources it was that we have. So this is a snapshot of what our data looked like for this competition. And we have a variety of runs that vary in difficulty, and also a number of those components. All right. So here are the 6 strategies that we use for a data competition. And so now 3, 4, and 5, let's revisit how this actually gets implemented for a particular scenario that we're looking at. And so this is a new kind of space-filling design. And even if you're thinking that you're never going to be associated with a data competition, this is a kind of design that may actually be useful to you just as we're collecting data in a number of experimental settings. So traditionally, what's happened is that we've said all regions in our space are of equal interest, but what if they're not? What if we have some supplementary information? So think of this as the peak of a mountain, and our interest is in more data here than as we get further away from that. So maybe it's an optimization problem, and we think our optimum is somewhere here. Collecting more data might be strategic there. So what we've done is we've provided a knob so that the experimenter can adjust the amount of non-uniformity that we have. So as we go from the left to the right, you can see that more points are moving towards the top of that mountain, and things are getting more sparse around the outer edges. So this is something that we can hand to an experimenter and give them control over how we're going to collect the data and where it's distributed. In terms of the mechanics of this, is the only page with equations in the whole top. Usually we talk about space filling designs in terms of Euclidean distance between the points. And so the only adjustment that we make is that now we have, for each of the points that we're considering, we have an associated weight for it. So a bigger weight says put the points closer together. And so effectively, if we have big weights in here, then that's going to make it look like the metric that we're using makes these points look like they're further apart than they actually are in the original Euclidean space. So it's going to bunch up the points that have big weights, and if we have smaller weights, we're not going to have that sort of spreading out impact of things. So a Maxi Min criterion, very easy to implement. We just have to say for each of the points, do we want to emphasize or de-emphasize? So this can be applied in a lot of different settings. So if we're trying to optimize a response, so maybe we know that that's going to be where our optimum lies, but we still want a little bit of space fillingness. If we have interesting features, if we built a model, we may have different amounts of variability in different regions. We want to put more data where we're less sure about things. Or if we have data and a computer model, there may be regions where those two things are not in sync with each other, and so we can emphasize and get more data where in fact there's a discrepancy. So lots of ways that this might be useful, and all that we need is to associate a weight that's sort of desirable or less desirable for that. For the data competition, here's how we implemented this. So we started off before the very first data competition, and we got the best available algorithm that we could. And we generated a large amount of simulated data for that, a superset, so it was actually 10 times as big as the 25,000 runs that we ultimately were going to give to the competitors. And we ran them through the data set through the algorithm. And so from this, we were able to generate the probability of correct prediction. And here are some of the parameters that are important. So here is the speed of the detector. So as we go from walking speed to driving speed, you can see that things get harder. This is on the y-axis, the signal to noise ratio. So higher on the plot, the amount of the source is bigger, and so that gets easier. So the top left corner, we're going slowly, and there's lots of stuff to give us evidence of detection. Bottom right corner, we're going fast, and it's a tiny amount that we're trying to detect. So that's sort of the easy and hard parts. And so we've constructed some contours that we're going to use as our weights to guide the construction of the algorithm. So here's what we ended up, the training, public, and private test sets. And if the colors here correspond to our different backgrounds, so it's actually 8 different designs that are superimposed on each other. And what you can see is for the training set, there's more of an abundance here of easy ones where we're providing the solution. In the public test set, you can see there's more data through the middle. So we're asking them to perform and give us answers, and this is where they're getting feedback. And then to pick the winner, we really want to see that they're going to do well in this most difficult space. So we've constructed the sequence of these data sets that we're going to provide to the competitors to have this progression built in. And so we did this actually, there's 288 designs that we needed. So this is for technetium with no shielding, 3 data sets there, and then we have it for the 8 backgrounds. And so we had all of these different combinations. So for the very first competition, we didn't have this methodology, and I hand constructed all of those designs by, just from scratch and looking at different properties. That was probably a 2-week effort to get that data set. This was done over a weekend where essentially we just set the computer up running after giving it some parameters for the search. So a real efficiency there, and these designs look much tidier than the ones that I constructed over a much more difficult time period. Okay, the last component before we're ready to launch the competition is in fact creating the leaderboard. And so we have all of these objectives. So detect, identify, locate, times 6 different sources, and then we also need to handle the no source runs to get the false positive rate at a level that's acceptable for usage. So we're bundling 19 different components together into a single metric. And so we want to make sure that we're rewarding the right behavior and punishing things that will not make it acceptable for operational things. So we had overemphasized the number of runs that had sources. We want to be able to model those. And so now we're going to correct for that. And so we're going to put a very stiff penalty on the no source runs. So getting a no source run wrong will hurt your score a lot more than getting a with source run wrong. We took a weighted average of these different components for the source runs, and then the no source runs are all or nothing. You either declared it correctly or not. And then to get the weighting part right, we just constructed a lot of different kinds of mistakes. So maybe I misidentified, maybe I mislabeled some of the source ones. How do we in fact get that? And we got our subject matter experts, our nuclear radiation detection folks, to come up with a ranking that matched those kinds of mistakes and felt like it got the ordering correct. All right, now we're ready to launch the competition. This is where we sit back and watch a lot of what's happening. And now after the competition, we've given out the prize money, but the real value in holding the competition is figuring out what happened in the different algorithms, where they're strong, where they're weak, how can we in fact understand what happened, and that's where there's some statistical pieces that we can use.
What was the prize money?
Yes, so first prize was $25,000, and the total purse was $100,000. So the 10th place person got $2,500 for this.
And these were individual competitors and not groups?
They were. So I think there was nothing that kept a group from competing, but it was hosted on Top Coder, and the culture was actually there that it's individual competitors.
So for the national labs, 100K.
Oh, no, so for the first competition, there was no prize money. A couple of them did compete, but they were not allowed to receive any prize money. But the flip side was we actually were able to pay some of the national lab teams in the first competition to put in some time to compete. So they got participation awards. The international competition needed actually results. Okay, so here are some of the reasons why, if we bundle those 19 criteria together, the odds are that in hindsight, we won't be very happy with what we chose. In other words, we won't have quite gotten the ordering correct. So we'd like to decouple things from that leaderboard scoring and be able to answer a number of questions. So in the input space, we're interested, is the detector going fast, more difficult to handle, or the amount of material being reduced? How do those impact the quality of the results? The strengths and weaknesses of each algorithm. Maybe an algorithm is very good at handling plutonium, but it's not as good at handling uranium. So we'd like to be able to disentangle all of that, and we can do that with some different analysis. So a couple of these will look very familiar. They're sort of the obvious things to do with what we've got. So this is a confusion matrix. So the rows correspond to our 7 different kinds of data. So in a particular row, all of those runs correspond to source 1 or source 6 or the no source runs. And then the columns correspond to what a single competitor chose for a particular submission that they made. So the dark green corresponds to correct identification and detection. The light green corresponds to correct detection, but they misidentified it as the wrong kind of source. And then the white ones correspond to having missed that source completely. So what this does is it gives us a nice compact way of summarizing across all of the competitors. So here are, for the first competition, the 10 top teams that we have, where the dark green corresponds to detection and identification. The dark blue corresponds to just detection, but misidentification. And this is the chunk that we have that were missed completely. So here are the results of our second competition. And the first bar here corresponds to the baseline that we had. So this is WaveRad, one of the detection algorithms, what its performance did on our data set. And then A through J correspond to first through 10th. These are the prize money winners that we have for this. And a couple of things should jump out at you. One, they're not monotonic as you go from first place to second place to third place. We're not getting just a slow degradation of performance, but these algorithms have different strengths and weaknesses that provide an opportunity for us to leverage what's going on there. This no source run, we do want to see lots of the light blue here. So those are runs that actually were no source and they were labeled as such. And you can see that we've got some that actually have probably a false positive rate that's artificially high that would not be satisfactory for actual use. Okay, what else can we get from this?
But just on that,
Yes.
normally, so this is like 2%. And of the runs, so you refer to total runs.
Yeah,
Normally you have like total numbering of 1 for 8 hours,
right.
whatever that really means in terms of number of runs. So that's pretty high.
Yes, and so each of these runs, so it's at maximally a half mile, and it was going between 1 and 13 meters per second. So the length of time for completing a run varies quite a bit, but it's a false positive rate that's still probably unacceptable for operational,
Yeah, it's like 10%, right? Out of 10%.
for the baseline.
So this is the winner.
No, so this guy is the baseline before
Oh,
we
that's
started.
baseline. Okay,
And
sorry.
so here, these are the sort of the
These
top
are-
4 competitors, and that's somewhere in the order of 2% false positive rate. Okay, we can also break it down into run-by-run performance. So again, we got the speed of the detector and the amount of source for all of these plots. The green symbols correspond to runs where this is the winning competitor's algorithm that we're looking at here. So all of the green dots are ones that were correctly detected and identified. The yellow symbols correspond to correct detection but misidentification, and the red ones were the ones that were just missed. So clearly, if we have no shielding for, this is the plutonium, if we find it, we know what it is, right? There's very few orange dots that we're looking at here. But as soon as we add the shielding, then it becomes a much harder problem in terms of identification. So this is already telling us some of the pieces. And if we're going to miss it, it tends to be for the very small amounts that we have and is relatively independent of the speed that the detector is moving. So already we're starting to see some patterns in the results that we're seeing. Okay, we can also dig a little more deeply to understand which in fact are the confusing sources. So what are we likely to mistake for one or the other? So top is the winning competitor, bottom is the second place competitor. And again, just reinforcing things that the red circles correspond to which of the competitors was best for a particular source. So they have unequal strengths and weaknesses. So the second place competitor was actually better with a lower false positive rate. So of the 2,800 runs, only 21 of them were misclassified, and we can see which sources they were confused with. So the off diagonals probably in this case are more interesting to us than the on diagonals in terms of which sources are mislabeled for each of those pieces. I haven't talked a lot about the locate part of things, so here is a summary that tells us how they performed on the different data sets. So the y-axis here is the average absolute miss. So if they said, I think this is the moment that the detector is closest to the source, on average, the first place finisher was missing by about 1.3 seconds. And this is not distinguishing between early or late. And so it's an unfair comparison. It looks like competitor 19 actually is the top performer here. But remember, they have to have correctly detected and identified the source. And so he probably has many fewer elements in this average that we've calculated for the locate than the top competitors who have actually been able to detect much more of what's going on. So a little bit tricky to interpret this one, but essentially we get a sense of how much they're missing. And you can imagine that this is a very skewed distribution. A lot of things near zero where they figured out exactly, and when they miss, sometimes they miss dramatically. All right, last is a model-based analysis. So here we want to go from sort of an exploratory data analysis to a more formal contour plots of what's happening. So for detect and identify, we use logistic regression. And so we put in terms for the size of the source, was it shielded or not, which of the different backgrounds we were looking at, which lane were we driving in, and then the speed of the detector. And across all of the different sources that we modeled, we got remarkable consistency. So it matters how much there is of the source to detect, is it shielded matters, and the speed of the detector. So those are the elements that we're going to use for modeling. It's very helpful actually that these things are not significant, right? We're going to be trying to exercise algorithms on different backgrounds, and if our algorithms were sensitive to those backgrounds, that would be a problem. It would mean that we'd have to adapt our algorithms depending on the background we're looking at. Similar pattern for when we're looking at the absolute miss. The only thing here is that the lane we're in does have an impact. So if the source is close to the lane that we're driving in, we have slightly better precision for the locate part of the problem. So again, a lot of these things feel quite intuitive when we interpret them. So based on that, we're able to generate a contour plot. So this is our winning competitor for the plutonium again. So lots of summaries for this. And this gives us now a summary of how well we're predicting across the speed and signal to noise ratio. And we've got with and without detection there. So the stronger signal is the single most important thing that's influencing things. As the detector goes faster, it gets a little bit harder, but you can see that these lines are more horizontal than vertical. And so that's telling us the amount of the source is a single bigger driver than the speed of the detector. And we can do the same thing for identify as well. So it's giving us the ability to look at each competitor's solution and see how they're performing. We can also compare within competitors and between competitors. So here, this is competitor one looking at their contour plot and subtracting off competitor two. So if we're in the blue tones, it says competitor one is better than competitor two for this space. And it gives us some calibration by looking at the colors for how much better they are. And so these are all sort of relatively small differences that we're looking at between the two competitors. But competitor one is clearly better than competitor two for probability of detect. For probability of identify, we have a small region where competitor two is actually better for this source. So it's giving us more nuanced interpretation of how these competitors stack up with each other. So this is just a straight difference. There are actually some more formal methods. So small differences may not be significant. And so we actually could do a probability of agreement analysis on here that gives us, are those differences big enough to be important in our assessment of the algorithms, or should we just group them together as performing similarly? Okay, last chunk, understanding the results of our competition. So between the first competition and the second competition, we learned quite a lot, things that we did not like as much in the first competition. So our background diversity was really not that diverse. And so we made the data sets richer and we varied things much more. So in the second competition that was open to everyone, we had a much wider suite of backgrounds that we were asking people to detect against. We also eliminated those big sources. If you look at the contour plots, there was a big chunk at the top where everyone was getting it right. Let's just get rid of those and focus on the regions where there's differences between the algorithms. And we also increased the penalty for false positives. In the first set of solutions, we had false positive rates that were not operationally relevant. Okay, here is the list of the top 10 places from our top coder competition, the second one. And you can see that it's a very international field. We originally were not sure that we wanted to show this list to our sponsor, There was an awful lot of Russian competitors that were performing quite well, and we weren't sure that giving prize money to Russians was necessarily something that our sponsor would be delighted with. But here are some of the improvements that we saw across the competitions. So the first competition, so this is the one that has government participants. From the initial baseline that we used to create the data set to the end of the competition, there was an 18.5% improvement in terms of how much the scores were changing and our ability to solve the problem. We then had the top two competitors from the first competition actually participating in the second competition and running those algorithms on the new set of data. And so this corresponds to the implementation of that piece. And from that competition to the end, we saw another 9.8% improvement in the score. So this is a little bit of a fiddle to put those two pieces together, but from the start of the first competition to the end of the second one, we might have seen somewhere in the ballpark of a 30% improvement in terms of the ability to detect and identify and locate. So this was quite satisfying in terms of driving the behavior of the competitors to actually respond to the challenges we put forward for them. And then here is a little bit about the winning algorithms that we have. So this is thanks to Tenzing Joshi up at Berkeley Lab. He's doing a more detailed analysis of the top 10 algorithms. They had to submit a white paper summarizing the key features of their algorithm. And so there were some surprises. So many of the competitors used a binned energy approach for things. I think in a lot of these algorithms that are used operationally, there's a dial that tunes the sensitivity with a changing threshold for detection and not detection. That was not something that was a key feature in these algorithms that we're using. Many of the approaches use neural networks. So this is primarily a machine learning community that we're using their algorithms to solve problems. And they were an ensemble. So many layers were being used to be able to sort out what's happening with things. It was also interesting to see what they did to the data that were provided to prevent overfitting or reduce the chance of overfitting. And so there was a lot of cleverness about just making maximum use of the data to be able to extract as much learning as possible from the training set, and then also to minimize their errors. The winning competitor was sort of head and shoulders above the others. From his very first submission, he was in first place. So that showed that he did quite a bit of training. And so there was a number of things that he put into his white paper that actually talked about making his algorithm operational. So there was a lot of insights here. Not someone who knew a lot about urban radiation search, and yet he was thinking about the problem in a way that provided some real insights that were helpful for extracting those features and thinking about using that. So I think in many ways this was a very successful competition in terms of the progress that we saw throughout the competition, but also the insights that we got of having data scientists look at this problem with a fresh set of eyes and creating, proposing some innovative solutions. Okay, data competitions are, I think, a real opportunity in lots of different realms, and I think they can really accelerate the improvements that we're seeing and lead to those groundbreaking improvements that we see with a whole new paradigm being brought into play. The designing of the data set, I think, is key for making sure that the right question gets answered and that there aren't any artifacts in the data that people are trying to avoid. And then I think it can also set up a more detailed analysis to get maximum value for that. The leaderboard is critical for driving the behavior that you want. And the post-competition analysis, I think we can really extract much more value from that than just getting a raw ranking of this one is best and this one came in second. A lot of competitions are sequential in nature, so that you host a competition, you learn something, and then move forward. And I think the post-competition analysis gives us a mechanism for extracting where improvements are needed. I mentioned a few things. The top two papers actually talk about the whole statistical elements of hosting a competition and extracting value. The non-uniform space filling designs, I think, are broadly applicable to many scenarios beyond data competitions. And then if we're going to do a more formal comparison of our algorithms across the space, those are some useful references here. All right, thank you.
Okay. Thank you for this very interesting presentation. It was quite interesting for me actually. Really interesting application of competition and research. I was curious what happened to the ownership of the algorithm. So in competition of journals that are based on the algorithm, are the original authors?
So I think we don't have a plan to publish anything about the actual algorithm. So far, what we published is the setup of creating the data and then also the competition itself. The competitors sign a declaration saying that they will maintain ownership of the intellectual copyright, but we get a copy of their code. So they're free to use their own code and modify it. But I think in terms of publications, we haven't thought about having publications that target the innovations that are in the algorithms themselves. Now that you say that, it does, who owns that is something that would be have to be careful with.
Both those algorithms and the author retain the right to use the algorithm.
Yes, yeah. So, and I think we have, so it's actually NA22 who owns the algorithms, and I think it's actually a quite limited usage. So expanding them or adapting them probably needs some permission.
I have a quick question.
Yeah.
Did you give any feedback to competitors after competition so that they know, where they were, what was the problem, and so on? Your analysis was available to them or not?
It has not been available to them, and I know as we do this analysis on existing algorithms, so ones that are operational, classification issues come into play. So exposing, we're really horrible at solving this problem is not something that can be broadly disseminated, but we have given no feedback to the competitors. They sort of, the flow of information has just been one to them.
I mean, maybe the first competition when you had labs,
Yes.
it seemed really important if you have such an analysis that shows what are good or bad things for particular algorithms. It's very important for further development.
So I will say this, let's see if I can find it. We did get a request halfway through the first competition for feedback. And so we provided a version of this for each competitor so they could see which of the sources they were doing well. And this was actually quite controversial for our team. I'm like, should we be doing this? Shouldn't they figure this out on their own? And then ultimately, we want just the solutions to evolve, so let's help them. But there was no talk of doing that for the open competition.
Okay.
Just to Luca's point, I mean, so certainly some of the participants, they can publish their work and can convert to that. I mean, that's pretty what we did.
Yeah.
I mean, there's nothing preventing them from publishing. Their algorithm actually even referred to that in this competition. Because again, it was a publication. And all, I think, the results are published, not just not the details.
Yes.
And I think one has to be a little careful there. So I think,
You have
yeah, I mean, so the baseline, so what was the baseline? That was an established tool?
So it's WaveRad, so is that something that means something to you? So and so I think it may not be a totally fair comparison because I think there's a lot of tuning that they might have been able to do with this. And this was a volunteer effort on their part. We just asked them if they could run it through their algorithm. And so I think with some tuning, they might have been able to get improved performance.
Because I think that was one of the challenges, getting people who've been working with them their whole life to compete.
Yeah.
Again, it's like your argument
Yes.
is that, oh, they believe they're the best because the data they're using, for them, it's that specific set.
Yeah.
The algorithm is the best, but some of them competed, some of them did not.
Go ahead.
Just to follow up on that, is it the baseline is the one that they use your simulated data set to validate their algorithm?
So,
I mean, do you give an example of what is that simulated data set that you have provided?
right, so they had exactly the same access to the training
The
set.
training set.
And they also, we didn't put any constraints on their ability to submit multiple times, right? So it wasn't just use your algorithm, submit once, we're done. They had the opportunity to tune, but I have access to the number of submissions that they made, and so they really just submitted 5 or 6 preliminary runs, and then they ran it through a number of different thresholds. So they made a total of 10 submissions. And so I think when you compare a competitor who submitted 200 submissions and was fine tuning, I think the level of investment to match the data to the algorithm.
To validate the algorithm.
Yes, what was probably very different for this wave grad.
Last question?
Yeah.
For a great presentation, thank you very much. One of the questions I had is, how do you see the usage of data compositions, competitions growing over time, especially in the private or rather the government sector?
So they are becoming much more prevalent. So I think if you look across banking and I mean, just all of these applications, the notion of crowdsourcing. So this, we gave $100,000 in prizes for this. And that was much, much cheaper than funding the first competition with however many teams that we had. Yeah. So there is a tremendous economy of scale. Like you have a fixed budget, you know what you're going to give in prize money, and then you get this overwhelming response. So back to the Netflix competition, they had that open for a couple of years, and they had thousands of participants spending hours and hours working on this, and they gave away $1 million. So if you put any sort of value on the time of the people developing algorithms, it's a really cheap solution, and it has a fixed cost. So I think many more groups are discovering what an opportunity that is to crowdsource things and to have these solutions. And I think occasionally a brilliant idea will walk through the door from someone just thinking about the problem in a fundamentally
Like
different way.
carpenter.
Yeah.
Okay, we have 2 actually.
Okay, yeah.
I mean, in that regard, I mean, there will tens of millions of dollars have been invested in the development of detection analytics, tens of millions of dollars, over the years for sure. 100K to figure out that actually the guy who's not the nuclear expert is probably eating everyone. That's certainly worth it, 100K. However, the question, and then of course there are many other IEA, we had just a really wonderful presentation last year, is adopting the crowdsourcing as well. Not necessarily in terms of data, but even instruments. Prevent you from doing it, I mean, even for the development and demonstration of even hardware and instruments.
Yeah.
So it's much more broadly applicable, the kind of outsourcing. And that's really realized in a really cheap way.
Yeah.
Because the international competition and the incentive to be the best worldwide is enormous, like Wikipedia and all that.
And in the government competition, I mean, there was no prize money. It was basically a handshake for the first thing. And one of the teams was, my colleagues down the hall. And, the emotional energy, and I mean, the competition closed at midnight, and they were submitting at 11:54. Right? So I mean, beyond work time, they were obsessed with that, and so that harnessing that passion.
Right, it's cool that you don't have a problem getting the.
Okay.
But what happened though? My question though is,
Yeah.
what would happen if you would have put $100 million?
Right.
It's like right now, the
Right.
everyone is not compete. Like really the leader in this field might not even have competed.
Sure.
Because they don't care about that. They have their own problems to solve. What would have happened if you would have?
Well, so we still would not have hosted it because it took a year to be able to get the.
No, and just in terms of the impact that you really have and tap into really
Yes.
completely different pool
Yes.
of experts in this field.
So I think that's an interesting question. what is the threshold
Yeah.
for getting everyone involved? And I don't know that it's always
Of course
about
not,
money.
but that's again why
yeah,
the work
yeah.
is, I mean, what would
But-
have happened though?
Okay, we have one last question, please. We are all over the time.
Have you already used open models together to try to build a, like a meta predictive model and see where one is lacking and the other one is getting better? Like to sort of understand, okay, and identify the source based on the they're getting the results. So build a sort of machine learning algorithm based on the algorithm itself.
So we, I have a partial answer to that one. So what we have done, let me jump ahead to this guy. So what we have done is we've looked at, suppose with perfect knowledge, we could just pick the algorithm that does best on a particular problem. So we've looked at, so of the 2,800 runs with no source, if we put together the top 3 and the top 5, does someone get the right answer for all of the runs? So we've done that for all that. So we've got sort of the runs that everyone got right, the individual competitors, and then we've got the superset solution that says if we could just magically pick the right algorithm to solve that problem, could we get the right run? And that's a pretty big envelope. Now, building the algorithm that actually can distinguish which of the algorithms to draw, I think that's what you want, and that's a much harder problem. But we at least have the bounds for what might be possible to approach if we had that knowledge. So we did fund, after the first competition, the top 3 winners to work together. And I think their approaches were different enough. There were things to leverage to build that super solution that was noticeably better. But yeah, the actual implementation is difficult, but we have a known upper bound of how well we might expect it to do with the combination of those top algorithms. So.
Okay, so thank you very
All right.
much. And you can stay and ask additional questions.